So far, we have discussed monochromatic plane waves. They have only one single frequency and their duration is infinite. If we wish to add information to this wave, it has to be modulated. In modulation, we change amplitude, frequency, or phase of the wave. Any modulation will then add more frequencies to the wave, and therefore its spectrum will be broad. If the material the wave is propagating has dispersion, then each of these frequency components will have different velocity, and the propagation of the pulse is affected. Now we shall analyze this process and its effects to the amplitude modulated monochromatic wave. On the left, we have a monochromatic wave in blue, whose amplitude is modulated by a pulse. Frequency spectrum of this pulse can be accessed by Fourier transform or discrete fast Fourier transform. In the frequency domain, the spectrum of the pulse consists of the carrier at the center frequency omega 0, and around it we have the spectrum of the amplitude modulation. This pulse then transmits through a linear system whose transfer function is h omega. The transfer function can affect both the amplitude and phase of the spectrum. The output of the system is a product of the spectrum and the transfer function. Transfer back to the time domain will reproduce our pulse and the carrier wave. This can be done by inverse Fourier transform or discrete inverse Fourier transform. Comparing the output from this system, we'll see that the modulation envelope of the pulse has shifted in time by the so-called group delay, and the phase of the monochromatic carrier wave has delayed by phi. These delays are related to the phase delay of the transfer function. Let's take an example of transfer function which has only a phase response. Actually, propagation of plane waves can be thought as multiplying the amplitude of the field with the transfer function containing the wave number and the propagation distance. In case of dispersive materials, the wave number k is often replaced by frequency-dependent propagation constant beta. And further, beta is dependent on the dispersive refractive index. From this expression, we can start to analyze what are the delays in the monochromatic carrier wave and the pulse amplitude. Let's first see what is the phase delay of the monochromatic carrier wave. By carrying out the Fourier analysis, we find out that it is the phase divided by omega 0. If we insert the phase from the transfer function, we have an expression like this. And if we now calculate the velocity, it is the distance divided by phase delay, and it is speed of light in vacuum divided by refractive index at exactly the operation frequency. So we'll see that the velocity of the monochromatic carrier wave depends only on the value of refractive index at that specific frequency. And this is called phase velocity. The time delay of the pulse amplitude, the group delay, on the other hand, depends on the derivative of the phase. Again, we insert beta and distance and carry out the differentiation. We can first take the distance and speed of light in front, and then derivative with respect to omega, and then the derivative with respect to refractive index is like this. And this expression in the brackets is called a group refractive index. And now we see that indeed the velocity of the pulse amplitude is different than the velocity of the carrier wave. And this velocity is called a group velocity, and it is often considered as the velocity that information can be transmitted by the modulated pulses.